VOR beacons have been guiding aircraft since the 1950s. Although the technology is pretty ancient, they do use some interesting concepts in analogue radio engineering, with a number of adaptations to cope with the shortcomings of the analogue basis upon which they work. In this video, I'll show how the beacon generates and transmits the navigation signals. It's not intended, by the way, to be a guide for pilots on how to navigate with a VOR. There are plenty of videos on the web that show that. This video is about the technical side of things at the sending end, and you'll need some understanding of radio engineering and electronics to make the most of it. VOR stands for VHF omnidirectional range. VHF and omnidirectional, fairly self-explanatory, but the word range perhaps needs to be clarified a bit. Mostly these days when we talk of range, we talk of range to target, range on full tanks. But in this context, the word range comes more from the home on the range meaning. It was used to name the system because of the previous use of the word in the 1920s and 30s. The term radio range was used to signify the airways defined by radio beacons, which in those days operated in the LF and MF bands. Most descriptions of how a VOR works start with an analogy with a lighthouse with a revolving beam of light, so I'll do likewise. Here's a lighthouse on a headland overlooking the sea, and it sends out a sharply focused red light beam, taking 36 seconds to do the full sweep around the horizon, so that it moves at 10 degrees per second. When the revolving light points due north, an omnidirectional white light flashes. All the mariner needs to do is to use a stopwatch to find the time between seeing the white north flash and the flash from the red rotating light. Here you can see the sailor on board our ship has his stopwatch ready and is looking through a telescope at the lighthouse for the white flash. When he sees that, he starts the stopwatch and then stops it when the red flash is seen. In this case, the stopwatch reads 12 seconds. We know the light beam is moving at 10 degrees per second, so to the ship it's 12 times 10, that's 120 degrees from due north. We say that the ship is on the 120 degree radial bearing from the lighthouse. So this system has two signals, a variable signal, the revolving light beam which varies in timing depending on where you are in relation to the lighthouse, and a north reference signal to show when the lighthouse is pointing northwards. VORs similarly provide a variable signal and the north reference, and the aircraft equipment electronically measures the time between these two signals in order to work out the radial the aircraft is on relative to the beacon. However, this analogy has to be taken with a bit of care. The VOR does not use a rotating, sharply focused beam of radio waves, for example, and the north reference signal is not provided by a short pulse of radio waves. Instead, VORs send the data out using two sine wave audio tones, and it is the phase difference between these two waves which determine the radial bearing the aircraft has in relation to the beacon. There are two types of VOR, the conventional VOR and the Doppler VOR. The conventional VOR was the original type installed in the 1950s. Initially it used an antenna involving a spinning dipole, spinning at 1800 RPM. But these were soon replaced with an all-electronic version which proved more reliable. These original VORs had some shortcomings, but there are many still giving satisfactory service around the world, particularly in the USA. To get over the problems, the Doppler VOR was developed and is probably the most usual one to see, certainly in Europe. I'll describe how the Doppler VOR works first, as its operating principle is somewhat easier to understand than that of the conventional VOR. But before I do that, it's worth introducing you to the antenna that has been almost universally used in VORs since their inception. Here is one of them ringed on a Doppler VOR. It's known as an Alford loop antenna, named after its inventor, Andrew Alford. He was born in Samara, Russia in 1904. He moved to the United States, graduating from the University of California in 1924. He worked on many antenna designs over the years, including broadcast antennas, and he was involved in development of the first ILS. In the 1940s, he received a patent for this antenna design for use in navigation systems. The Alford loop has the useful attribute of omnidirectional, horizontally polarized radiation in a fairly simply constructed and quite broadband arrangement. To understand the configuration of the Alford loop, look down in plan view on a simple half-wave dipole, with the red dots representing its feed point. Now turn its two arms to a 90-degree angle. Move it to one side and put another identical antenna as shown to form a square configuration. We join the two together to get a single feed point and swap over the connections to one antenna to retain the required phase relationship. Now the current distribution in each quarter wave element would look like this, with a current node at the end. However, Alford improved the current distribution by adding capacitive loading at the end of the element as shown. The current distribution is now more like this. The average current is higher, resulting in more useful radiation from the antenna. The end plates can also be made variable in spacing to allow the element to be tuned to the operating frequency. If we now feed RF to the feed point with relative instantaneous phase as shown, it appears like this at the ends of the elements due to the transposition of the feeders. Now if we show the current direction, you can see that the currents in the four elements flow in the same direction, and so a distant receiver gets an in-phase signal no matter what direction horizontally they are from the antenna. This is what gives the antennas good omnidirectional characteristic. I found it interesting to look at Andrew Alford's original patent application, granted in 1942. This is the diagram with the nub of the invention. There are the four radiating elements arranged in a square. These are the capacitive end loading, and that's the feed point, and there is the feeder transposition to get the correct phasing. Lastly, and somewhat confusing to me at first, he shows a graph of the current distribution by these shaded areas, and also the instantaneous current direction by the arrows. The actual Alford loops are typically covered with a fiberglass radome, although not in the conventional VOR, which uses a single overall radome, as we will see later. The radomes, as you could see in the picture showed earlier, have a triangular dome configuration to aid in shedding of precipitation, rain and snow, etc., which might affect its operation. If we remove the radome, you can see the typical construction of the Alford loop. The elements and feeders are constructed from sheet metal, such as aluminium or brass, which gives good mechanical stability and helps to give the antenna a broadband characteristic. It also allows easy alteration to the spacing of the capacitive loading plates to tune the antenna. The elements are typically around 100 mm deep as shown. The feed point is connected to the transmitter equipment by coaxial cable via suitable balun and matching elements. And before we look further at the principle of the Doppler VOR, let's see who it's named after. Christian Doppler was an Austrian scientist born in Salzburg in 1803. He studied mathematics and physics. In 1842 he gave a presentation showing how the varying colour of moving stars could be explained by the relative motion between the stars and Earth. The Doppler effect, where the frequency of electromagnetic or indeed sound waves varies with relative motion between the source and the observer, finds many uses in the modern day. From the use here in VORs, there's radar speed guns, radio direction finders, weather and air traffic radars. And the effect even has to be taken into account when using, for example, satellite communications in low Earth orbit, where satellite speeds can be quite fast. Here's a short audio demonstration of the Doppler effect. So back to the Doppler VOR. We start with a black dot here which represents an antenna connected to a VHF transmitter operating somewhere between 108 and 180 MHz, a wavelength of around 2.5 meters. The antenna radiates omnidirectionally with horizontal polarization. Now we make it move in a circular path. If we listen to the signal using a receiver with a BFO, it might sound a bit like this. An aircraft out to the east, right of the screen, will see a small change in received frequency due to the Doppler effect. As the antenna moves towards the aircraft, the frequency increases, and it goes away from the aircraft, the frequency decreases. Let's look at 4 particular positions on the antenna's circular path. Here the antenna is moving perpendicular to the line from the aircraft, so there is no relative motion and the Doppler effect is 0. The aircraft receives the unchanged carrier frequency. Here the antenna has maximum velocity towards the aircraft, so this is where the highest frequency of Doppler effect is detected. Here again there is no relative movement, so the Doppler shift is 0. And here the lowest frequency occurs because the antenna has the maximum velocity away from the aircraft. If we plot these 4 positions on a graph against time, we get this. If instead of taking just 4 points per rotation, we consider all points on the antenna's circular path, we get a sine wave. In the VOR, the antenna rotates at 30 times a second. The signal created is a 30 Hz sine wave, with frequency modulation having a deviation of 480 Hz. The antenna has to move around a circle with a diameter of 13.5 meters to give this deviation due to the Doppler effect. If the aircraft is further south, you can see that the positions of maximum and minimum antenna velocity move, so the resultant sine wave is slightly advanced in phase. So you see that the position of the aircraft changes the received phase of the FM signal's modulation. This is the variable signal that we talked about in relation to the lighthouse analogy. The phase depends on where the aircraft is in relation to the beacon. However, receiving a 30 Hz sine wave by itself is of no use. We need a north reference signal to compare it against. This is provided by another omnidirectional antenna, located in the centre of the ring that the variable signal moves around. This transmits a 30 Hz sine wave signal using AM on, in effect, a slightly different radio frequency. This signal has the same phase as that which an aircraft would receive from the variable signal if due north of the beacon. Now we have 2 signals as shown here, the variable signal above and the north reference signal below. All the receiver has to do is to calculate the phase difference between the 2 sine waves. It takes the same point on each waveform, for example the negative going 0 crossing here on the reference waveform, and here on the variable signal. This time difference is expressed in degrees and gives directly the number of degrees from north the aircraft is, the radial bearing from the beacon. This usually, by the way, is expressed as a magnetic bearing with respect to magnetic north, except for a few VORs in polar regions where magnetic compasses are not of much use anyway. It's not practical, however, to have a mechanically moving antenna on a 13.5 meter diameter. The circumferential velocity will be over 4,500 km an hour at 30 revs per second, several times the speed of sound. Instead, a large number of separate antennas in a circle are fed with RF power sequentially. They are commutated or switched so that the movement of a single antenna is simulated in a series of steps. As long as there are enough antennas, the aircraft receiver produces a good 30 Hz sine wave after filtering. And most Doppler VORs these days use either 48 or 50 antennas. This shows a graph of what a received Doppler VOR transmission would be, with 48 steps making up the sine wave. After filtering in the receiver, a good representation of a sine wave is achieved. The physical construction of a Doppler VOR is as follows. A large circular or near-circular ground plane or earth counterpoise is provided. This is typically 30 to 45 meters diameter and is usually of a suitable metal mesh construction on a steel framework, held about 4 meters above ground. Underneath the counterpoise is the equipment shelter where the transmitter equipment is located. The 48 or so Alford loop antennas generating the variable signal are arranged in a circle with a diameter about 13.5 meters in the center of the counterpoise. This diameter is critical to producing an FM signal with the correct deviation of plus or minus 480 Hz. In the center of the ring of antennas is a single Alford loop which radiates the omnidirectional north reference signal plus the ident tone and any speech signals using AM. Here is an aerial picture of the Trent VOR in the North Midlands of the UK. and this is the Pole Hill VOR in northern England. The antenna marked here, by the way, has nothing to do with the VOR itself. It's for the co-located DME, or distance measuring equipment. You can see the way in which the counterpoise is supported above ground with the equipment shelter underneath. Let's have a look at the Doppler VOR's frequency spectrum. Both variable and reference signals are actually carried on an AM transmission, although the variable signal is an FM subcarrier. In the centre is the AM carrier frequency, somewhere between 108 and 180 MHz with a channel spacing of 50 kHz, although the bottom 4 MHz of the band is shared with ILS installations, so only certain frequencies are available to VORs here. For clarity, we'll just look at the upper sideband initially. Next, there is the 30 Hz sideband, which provides the north reference signal. The 9960 Hz subcarrier carries the variable signal as a space-modulated FM sine wave, also of 30 Hz modulation, with a deviation of plus or minus 480 Hz. Next, there is the 1020 Hz ident tone, keyed with the Morse code identifier. And finally, if provided for, there's the speech signals occupying the band from 250 to 2500 Hz or so above the carrier. Speech transmission is not always used, but if it is, it could give weather or similar operational information to pilots. Of course, as for any conventional AM transmission, there is a symmetrical lower sideband emitted as shown. The modulation depths in the far field where space modulation occurs is normally 30% for the 30 Hz sideband's north reference signal, 30% for the FM subcarrier variable signal, and 30% for the speech waveform if used. The ident signal is nominally 7% modulation depth. As shown here, the north reference, ident and any speech signals are radiated from the central omnidirectional antenna, and the FM subcarrier is radiated from the commutated antennas in the ring. This demonstrates the commutation of the 48 antennas in the ring. Some Doppler VORs, particularly older systems, only switch one frequency, shown here as FC plus 9960 Hz. These therefore only produce one sideband for the FM subcarrier, and are therefore called single sideband VORs. Unfortunately, some aircraft receivers cannot cope with this signal. Accordingly, most modern VORs are double sideband equipment. Two RF signals, one FC plus 9960 Hz and the other FC minus 9960 Hz, are switched into diametrically opposed antennas at any one time. One signal is retreating from the aircraft and produces negative frequency shift, while the opposite antenna is advancing towards the aircraft and produces positive frequency shift. This gives the correct phase relationship between the sidebands for satisfactory space modulation of the signal. Of course, this complicates the commutator circuitry, as every antenna has to have provision for two signals to be switched to it, each at the appropriate time. Let's have a look at what makes up a Doppler VOR transmitter. We start with a 30 Hz sine wave generator. This is added to the output of the 1020 Hz ident tone generator keyed with the Morse code ident signal, and together with any speech is fed to an amplitude modulator. This amplitude modulates the carrier signal to produce a conventional AM signal with full carrier. This is then amplified up to 50 to 200 watts carrier power and fed to the center Alford loop antenna to give the omnidirectional signal. The carrier generator also produces the FC plus 9960 and FC minus 9960 Hz signals. These need to be coherent with the carrier so that when the space modulation occurs, the FM subcarrier is properly constituted. This means getting the correct frequency and phase relationships. The two sideband frequencies are again passed through RF amplifiers to give somewhere around 25 to 50 watts, which allows for power losses in the commutator and cabling to the 48 antennas. So the RF side of the Doppler VOR transmitter is quite simple. However, this is made up for by the commutator control electronics. This must appropriately sequence and provide the drive signals for the pin diode RF switches in the commutator. I've shown here a dotted line marked 30 Hz sync. This signifies that somehow the 30 Hz reference sine wave and the 30 revs per second commutation speed must be locked together. I've shown a variable phase shifter in the output of the 30 Hz generator. This allows the precise difference to be set between the commutation signals and the reference to allow for calibration of the nav aid against magnetic north. Lastly, a look at the commutator. For the single sideband equipment, this consists of a single pole 48 throw rotary electronic switch. The switchways connect to the 48 Alford loop antennas via coax feeders with identical electrical lengths. The switch rotates in effect counterclockwise under the control of the commutator control signals. The double sideband VOR complicates matters by using a double pole 48-way switch with the two upper and lower sideband frequencies fed to diametrically opposed antennas in turn. As I mentioned before, most commutators make use of semiconductor pin diode RF switch elements. This discussion of the commutator is somewhat simplified. In practice, there is usually an element of blending which occurs in the changeover between active antennas. One antenna reduces its RF output as the next one is increasing. This smooths over the steps in the Doppler FM waveform somewhat. Another aspect which needs to be addressed is spurious mutual coupling between antennas in the ring due to their close spacing. This induces parasitic currents in the antenna elements which then radiate, causing some disruption to the omnidirectional character of the transmission from the active antennas. This tends to cause unwanted AM on the FM subcarrier, and precautions have to be taken to minimize this effect to keep below the maximum specified 40% AM on the FM subcarrier. Now we'll look at the conventional VOR. You'll see from this fairly early example from Australia that it is much more compact in size compared to the Doppler VOR and is correspondingly considerably cheaper. The antenna system is mounted on top of the equipment shelter. The roof of the shelter forms a small earth counterpoise for the antenna. Let's begin by examining the frequency spectrum of the conventional VOR, as its use of the various signal elements is somewhat different compared to the Doppler version. This time the carrier with its 30 Hz sine wave sidebands provides the variable signal, which varies with space modulation around the beacon. The phase of the 30 Hz modulation depends directly on the azimuth bearing of the aircraft in relation to the beacon. The north reference signal, a 30 Hz sine wave, is FM modulated onto the 9960 Hz subcarrier with a plus or minus 480 Hz deviation, as for the Doppler VOR. Identically to the Doppler VOR, the keyed ident tone and any speech are also transmitted on the carrier. The conventional VOR uses 4 Alford loops arranged in a square formation. All signals, except the 30 Hz sidebands, are radiated omnidirectionally from all 4 of the installation's antennas fed in phase. The variable signal, 30 Hz sidebands, are radiated from pairs of antennas fed in antiphase and fed with 30 Hz modulation in quadrature, which produces a rotating figure-of-8 pattern. At this point it will be useful to compare the two types of VOR, Doppler and conventional. As you can see in this table, the north reference signal in the Doppler VOR is carried by the 30 Hz sidebands of the AM signal, whereas in the conventional VOR this is carried on the FM subcarrier. The variable signal is carried on the FM subcarrier for the Doppler VOR and on the 30 Hz AM sidebands for the conventional VOR. In order for receivers to give the correct bearing information, it's arranged that the conventional VOR rotates its variable signal clockwise, whereas the Doppler VOR uses counterclockwise rotation. The conventional VOR employs 4 Alford loop antennas arranged as shown, side by side in a square formation. They're typically annotated as shown here as northwest-southeast and northeast-southwest, as this is how they're fed with RF as 2 diagonal pairs to give the variable signal's rotation. The antennas are protected by a fiberglass radome, as you can see in the Australian picture. To radiate the reference, ident and speech signals, an omnidirectional pattern is required, and this is done by driving all 4 antennas in phase. To give the required figure-of-8 pattern, the diagonal antennas are connected in antiphase. We'll see a little later how these signals combine to give the required variable signal by space modulation. There's an important requirement for satisfactory operation of the VOR. That is ensuring that the signals are horizontally polarized with no significant vertically polarized waves. This is important because vertically polarized waves can cause incorrectly phased signals to be received when an aircraft banks away from straight and level flight. To get over the problem of the small amount of vertical polarization emitted by the Alford loops, a set of parasitic elements is provided called the vertical polarizer. We look at a cross-section of the conventional VOR antenna system. There's the earth counterpoise and then the Alford loop antennas. whole lot is enclosed in a fiberglass radome as mentioned earlier. Above the Alford loops, a set of vertical elements is mounted. These have adjustable length elements using tubing of two diameters, one sliding over the other. These elements are parasitically energized by the vertically polarized component from the antenna system and re-radiate the signals acting as parasitic elements. The position of the vertical polarizer above the Alford loops can be adjusted up and down, and the element lengths can also be adjusted as shown to resonate the parasitic elements to give the required cancellation of the vertically polarized waves. Now let's have a look at the conventional VOR transmitter. As with the Doppler transmitter, we start with a 30 Hz sine wave audio generator. This frequency modulates a 9960 Hz oscillator to give an FM signal with 480 Hz deviation. This is added to the 1020 Hz keyed ident tone plus any speech waveform to an amplitude modulator which provides an AM signal using the carrier generator FC. This AM signal is then passed through an RF amplifier to give the required output carrier power between typically 50 to 200 watts. This signal goes via the RF distribution shown here in the blue box to feed all four Alford loops in phase to give the required omnidirectional signal. Next we take the 30 Hz signal and produce sine and cosine versions of it, that is in quadrature or 90 degrees out of phase. These feed into two balanced modulators as shown. Each output is a double sideband suppressed carrier DSPSC signal with the carrier frequency suppressed in the output and just the two sidebands remaining. Again, the signals are amplified and sent via the RF distribution to the antennas. In this case, however, the RF to the antenna diagonal pairs is fed in antiphase to give the figure of 8 patterns required. In addition, the modulation on the two DSPSC signals is in quadrature or 90 degrees apart. This gives a rotating radiation pattern as required to generate the variable signal by space modulation. Lastly, there needs to be a means of varying the relative phase between the reference and the variable signal so that the beacon can be calibrated against magnetic north. Let's look in more detail at the RF distribution in the blue box above. First, here are the four Alford loops. Remember, in real life they are in a square side-by-side formation. Each one has a feeder and diagonal pairs are connected to an RF bridge or hybrid splitter. The hybrid splitter or RF bridge works as follows. It consists of a ring of feeder, typically coax cable as shown. Three sides are a quarter wavelength long electrically, and the fourth side is 3/4 of a wavelength. The four ports are shown here. There are two output ports, labelled here as P1 and P2, which connect to the antennas. The other two ports are for inputs. The top one is the summing port, otherwise known as the sigma port. The bottom input port is the difference port, or delta port. This works as follows. If power is fed into the sigma port, it splits equally in power and travels by quarter wavelength of feeder to the two output ports. The outputs are thus in phase and of equal power. The power travels half a wavelength to the delta port by this route and one wavelength by this route. The signals at the delta port are therefore 180 degrees out of phase and thus cancel. This means that no power is fed out of the delta port, which is in effect isolated. If we now consider power fed into the delta port, it splits equally again in power. Half travels over a quarter wavelength of feeder to output P1 and 3/4 of a wavelength of feeder to output P2. This means that the P1 and P2 outputs are equal power but 180 degrees apart in phase. The same consideration as before applies when considering the power fed towards the sigma input. Power from the delta ports cancel out, so the sigma port is effectively isolated from the delta input signal. To summarize, input to the sigma port gives outputs in phase, while input to the delta port gives output signals in antiphase. This is precisely what we need to drive the antenna system in the conventional VOR. The sigma inputs are connected together as shown and fed with the main AM output from the transmitter, carrying the north reference FM signal, ident and speech. This signal passes to all four antennas in phase, resulting in an omnidirectional radiation of these signals. The DSPSC sideband signals are fed to the delta inputs to each diagonal pair of antennas to give the required 30 Hz modulation components in quadrature. And remember, the sigma ports are isolated by the cancellation in the RF bridges, so the relatively high power of the main transmitter can't affect the DSPSC amplifiers. This diagram shows how orthogonal or 90 degrees phase shifted sine wave signals produce a rotating vector, the black vector in the center of the screen. Going back to the conventional VOR antenna system, if diagonally opposite antennas are energized out of phase, a figure of 8 pattern arises. When the other pair of antennas is added, and remember the modulation is 90 degrees apart in phase, a resultant figure of 8 pattern rotates about the center of the beacon's antennas. It rotates at 30 revs per second clockwise. An aircraft out to one side of the beacon will experience 2 peaks or maxima in radiation, as you can see, resulting in a 60 Hz signal instead of the required 30 Hz. However, if we consider that this figure of 8 pattern is combined in the far field with the omnidirectional carrier signal, by space modulation we get this radiation pattern. It's known as a limison. It has the form R equals A plus B cos theta. As this rotates, the variation in amplitude produces a sine wave at the rotation frequency of 30 Hz. You can see this has one maximum or peak level, so the resultant signal of the aircraft is 30 Hz sine wave. There's one major problem that arises with VOR beacons due to the analogue nature of their operation. That's multipath propagation of the signals. Here's a VOR station. Its direct ray reaches an aircraft some way away, as you can see. Unfortunately, there is a signal which is reflected from a building which is off to one side of the direct path to the aircraft. Many things can reflect the VHF radio waves used by VORs. For example, metal fencing sited in an unfortunate direction can also cause problems. The reflected rays are usually much smaller in amplitude than the direct ray, but they still cause some cancellation or enhancement of the analog signal. In effect, the phase of the received signals is changed, resulting in an error in the displayed navigation data. The diagram shows so-called lateral multipath. Objects to one side or another of the direct path to the aircraft cause the problem reflections. There can also be reflections from objects and particularly terrain in line with the direct path. This is called longitudinal multipath. This is particularly a problem with mountain or cliff top installations as shown here. Reflections off the valley bottom cause a problem at the aircraft. Even worse is if the signal is reflected off the sea. At the 2.5 meter wavelength of VOR signals, the sea acts as an excellent reflector which can cause severe cancellation of the VOR signal at certain distances from the beacon. A solution in this case may be to move the VOR further back from the cliff top so that the sea is not illuminated, thus eliminating the reflected signal. Lateral multipath is the most common problem encountered, and it is worse with conventional VORs. As shown here, an aircraft can be in the area of reflected signals for a considerable time period, causing problems with the received 30 Hz phase for perhaps several cycles of the 30 Hz. The Doppler VOR, in contrast, switches between antennas to produce a 30 Hz variable signal. As the effectively rotating antenna moves several wavelengths during each cycle of the 30 Hz, it's likely that only a small part of the 30 Hz waveform will be affected by the reflection, making any error in bearing much less noticeable than with the conventional VOR. This diagram is taken from an ICAO publication. You can see quite fast variations in coarse deviation output. This is called scalloping. Longer period errors are referred to as bends. You can see quite large errors can occur, 3 degrees for individual occasions of scalloping or bends, or as much as 6 degrees when both bends and scalloping occur in the same place. This level of error can in particular make landing approach guidance using a VOR to be untenable in some cases. The VOR is in some respects an unsatisfactory technology, mainly due to its analogue nature, and therefore its susceptibility to problems and errors due to multipath propagation. It's interesting that the benefits that pulse techniques would bring was recognized as early as the 1940s. With pulse signals, only the first received pulse is taken into consideration. Pulses arriving later can be ignored with potentially big improvements in performance. But the VOR is a child of its time. In the late 1940s, analog technology was well understood, and in particular, it was relatively easy and cheap to build the aircraft receivers, even if they had to use vacuum tubes or valves. Once aircraft fleets were equipped with VOR receiver technology, the inherent conservatism of the airline industry took over and has prevented significant changes until the recent widespread adoption of GPS systems. VORs have adapted over time. The conventional VOR started out with an electromechanical system involving a spinning dipole, later converting to an all-electronic implementation, as we talked about earlier. But the big improvement was the widespread adoption of the Doppler VOR, which significantly reduced the effects of multipath propagation. However, this came at a considerable cost penalty, with the need to provide a bigger site, many more antennas, bigger counterpoise and so on. However, despite these points, VORs have been good enough in performance terms, and their reliability in providing safe guidance to aircraft for the past 65 years or so should be recognised, even if it's been at some cost. They're likely to go out of use in the coming years as GPS and augmented GPS satellite systems become more widespread, but VORs remain an interesting and clever implementation of analogue radio engineering techniques. And I wonder if Andrew Alford would be surprised that his invention, pioneered and patented in the 1940s, is still in widespread use well into the 21st century, and derivations of his idea are now finding use in things such as Wi-Fi and cellular phone technology.